Hi everyone! In this video, we'll discuss Fick's second law of diffusion. We already know that diffusion is the movement of atoms or particles from a region of high concentration to a region of low concentration. Now, let's see how this process changes with time, leading to non-steady state. Before we get to the second law, let's quickly recall Fick's first law. It states that the diffusion flux, J, is proportional to the concentration gradient, given by the equation shown. This law applies to steady-state diffusion, where the concentration profile is shown by a straight line with decreasing slope and does not change with time, meaning the system has reached equilibrium conditions. Laws of diffusion were given by Eugen Fick, a German physician and physiologist, in 1855. Today we'll derive Fick's second law starting from a simple control volume inside a diffusing medium. Imagine a thin slab in which atoms are diffusing from higher concentration, left side, to lower concentration, right side, of the slab. Thus, concentration decreases along length x. Now imagine a small region of area I and volume delta V, cut out along the x direction of length delta x. The concentration profile slopes downward, so flux at the left face is different from the flux at the right face of this small cross-sectional volume. Imagine that the flux entering in this cross-sectional volume is Jx and flux leaving is Jx plus delta x. Flux at a point at any time in this small volume is changing with time, thus leading to non-steady-state diffusion. Thus, by plotting concentration versus distance, we get a curve whose slope is given by spatial derivative of concentration with respect to distance, x. We know that flux is mass of atoms per unit area per unit time. Thus, using this, we can write flux entering in region shown by delta x as Jx multiplied by area and time delta t. And flux leaving in delta x is Jx plus delta x multiplied by area and time delta t. Now flux accumulated in region delta V in time delta t can be calculated by subtracting mx and mx plus delta x. It comes out to be minus delta J multiplied by A and delta T and is shown by blue color. Now, recall that flux is directly proportional to concentration gradient and we have calculated the value of delta M. So we have to think of writing concentration in terms of mass and volume. In diffusion theory, concentration is defined for an infinitesimal control volume delta V around position delta X and time delta T. So we can write concentration as the ratio of delta M indicating the mass of the species inside volume delta V. Now you can use the already derived value of delta M. And by rearranging we can write delta C divided by delta T equals to minus delta J divided by delta X. We need to convert this into differential form so that we can find value at any point of interest. Taking limit on both sides, we get del C divided by del T equals to minus del J divided by del X. Now in this equation we can put the value of flux, J, from the Fick's first law of diffusion, then we can get the equation of Fick's second law of diffusion relating first derivative of concentration with respect to time, T, to the second derivative of concentration with respect to distance, x. Thus I hope you have developed an understanding about the Fick's second law of diffusion. More description about the concentration curve behavior will be discussed in the next video. Thank you.